Okay, so good afternoon or good morning, everyone. Thanks for dialing in. Our presenter today is Kristen Luchsinger from New Mexico State University, but joining us from Alaska today. And Kristen is going to be talking to us today about some work she's been doing modeling the L-cross impact and other lunar volatile related problems. So I will hand it over to Kristen to maybe introduce herself in more detail and to tell us more about her research. So Kristen, whenever you're ready, go ahead and take it away. And I will just remind everyone who is not Kristen to please mute yourself unless you're speaking. And feel free to have your cameras on or off, whatever you're comfortable with. And Kristen, would you prefer if we interrupted you with questions, or would you prefer if we wait till the end?
Go ahead and interrupt if you have questions, and I'll be happy to answer questions at the end as well if you'd rather hold them. Either way is fine with me.
All right, sounds good. Whenever you're ready, take it away.
Awesome, thank you so much. So thank you everyone for having me. My name is Kristen Luchsinger. I'm a fourth year graduate student at New Mexico State University in the astronomy department. And today I'm going to be talking about two topics. One about the work published in a recent paper about modeling the L-cross impact. And then also I'm going to be introducing my dissertation topic, which is modeling vertical volatile transport in seasonally shadowed regions. So I'm going to start off with my work on the L-cross impact and then transition a little bit later. So the L-cross impact was a 2009 impact mission into Cabeus crater, which I've illuminated here with this arrow. The impactor was a Centaur rocket associated with the launch of the Lunar Reconnaissance Orbiter. When it impacted, it excavated up to about 10 meters of regolith into a debris plume, which a shepherding spacecraft took spectra of while flying through this debris plume. So this was the first definitive and still the most definitive detection of H2O at the lunar poles. It was a really interesting and exciting mission, and it gave us a lot of new information about the interiors of these permanently shadowed regions. So the shepherding spacecraft spectra detected volatiles, including H2O specifically. This was the first confirmed detection of lunar H2O. And so this taught us a lot about, it confirmed the presence of water ice in these permanently shadowed craters and gave us a lot of information about, what was the possible source of this water ice, what other volatiles are here. So this was really groundbreaking in a lot of ways. During the impact, a number of ground-based observatories participated in observing this plume in support of the mission. What I'm going to be talking about today is ground-based images taken by Apache Point Observatory using the 3.5 meter Astronomical Research Consortium telescope. And these are images after being filtered through a principal component analysis program. So they had to be filtered through this PCA analysis because initially none of the ground-based observations actually detected the plume. But once they were filtered through this PCA analysis, as published in Stricker et al. In 2013, you see here, this is the PCA filtered plume detection. And then they also published synthetic modeled plumes that they also pass through the PCA filtering process. And so this synthetic plume is a new version of the synthetic plume is going to be what I'm going to be talking about today. So the synthetic plume is designed to mimic empirically measured plume kinetics that were measured by Hermelin et al. In 2012 in experiments at the NASA Ames vertical gun range. So we have a log linear initial velocity distribution, and we have three components, a low angle, a high angle, and then a very central plume. And so I'm going to be mimicking this empirically measured type of plume. I'm not deriving my synthetic plume from first principles. I'm just trying to mimic the appearance and behavior of this experimental hollow cylindrical impactor plume. So the previous model, which was published in Stricker et al. In 2013, in order to match the data, which is a time series of light curves. So you have, here you have by time, the normalized brightness, or the counts in this case. And so the black line is the data, and each of the boxes is a different pixel across the plume. So you have here, the edges, lower counts of the actual plume, and the peak is, in the middle. But in 2013, the data had a lower signal to noise, and so you couldn't really model the edges very well. Since then, Paul Stricker has been continuing to reanalyze the piece and readjust the PCA filtering pipeline. And we now have PCA filter data that gives us a higher signal to noise detection of the plume, which allows us to model further out to the edges. We can now select pixels that are further to the edge of the plume and fit the model, covering a greater swath of the plume, which gives us a much better opportunity to model in detail. So here you can see these are the pixels selected in 2013, and these are the pixels that I've selected for the 2020 work. You can see that we're going further out to the edge of the plume, and also that the pixels are on a finer spatial scale. This is possible because the signal to noise is so much higher in this new reanalyzed PCA pipeline data. So the new model, instead of truncating the initial velocity distribution, what I decided to do was use a stratified lunar sediment model. So my model variable now is the depth of the layers of boundaries, of boundaries of the layers. And when I say layers, I mean layers of material with different albedos. And so that's really what I'm modeling in this case, stratified lunar sediment, where a higher albedo corresponds to a higher water ice concentration. And I'll go over what possible layers I have in this slide here. So you can see the light blue corresponds to a mixed water ice and regolith layer. The gray corresponds to pure regolith. The hashed light blue corresponds to a mixing region where the water ice concentration either increases or decreases with depth. And the black corresponds to material with an albedo of 0. So I call this a bedrock layer, but it's not necessarily bedrock. It's just any sort of material with an albedo of 0. That means essentially material that was not ejected that should have been, material that was missing from the plume. And here I show the chi-squared per pixel for each of these models. So if you remember, there were 2 layers, and then as you get further out, you're getting towards the edge of the plume. So you can see that there's consistently a higher chi-squared in the lower left. This is actually because of the shape of Cabeus crater. The ridge kind of goes up in that area, so the signal to noise of the plume is generally lower, and so you get generally higher chi-squared. So that's going to be consistent across all of the models. What we're really interested in is looking at, here for these 3 regions, you get a very similar pattern of chi-squared. With the models with no ice or the model with no bedrock, you get a very different pattern of chi-squared, and it doesn't fit the time series of images as well in general. So in order to fit the data well, your model really wants to have some kind of ice, and the model wants to have missing material after about 6 meters of depth, which is the most statistically significant model feature, is having missing material after 6 meters. And here I show the model fits to the actual data in that center lower panel, which we saw was the panel with the lowest chi-squared in general. And so you can see the 3 models that I showed as being very similar, in fact, look very similar. Changing the behavior of the water ice doesn't change too much in the model itself. But if you try to remove the missing layer region, you really don't fit the later time series of images very well at all. And so that's strong confirmation that in fact you have to be missing material in order to fit the ground-based observations. Here I also present the calculated water ice percentages based on the model, and our best fit selecting a regolith density, selecting an albedo of water ice, is about 8.2%. And that doesn't disagree with previous works. I selected a different regolith density than previous works had used, but for the most part, it's all in the same ballpark. However, the statistical significance of the different water ice behavior models isn't super strong. So it's not a great choice to select just one. So I presented pretty much all of the possible water ice percentages to give a better sense of, as the water ice behaviors change, how does the ultimate water ice percentage change rather than just presenting this 8.2%, because that's not statistically significant enough for me to try to say this is the actual water ice percentage in Cabeus crater. I thought it was more interesting to present all of the possible water ice percentages and talk a little bit about, how our different choices and assumptions change dramatically what we calculate for water ice percentage. So I mentioned this missing material, and this is the most statistically significant result from this paper. So what is it? I call it a bedrock layer. It's unlikely to be a bedrock layer. It's only 6 meters deep, and we really don't expect to see bedrock that shallow. Could it be a layer of large boulders? This is possible, but there's no direct evidence for large boulder ejection during this event or for a significant layer of exclusively boulders at 6 meters. So I'm not really sure if this is a great solution. What I think is really interesting is it might be a cold water ice or a cold water ice and regolith mixture. So if you have a mixture of ice and regolith that has at least an 8 to 10% by weight water ice percentage, at very cold temperatures, it might have a hardness approaching concrete, which is fits very well with this missing layer that we found fits the data very well. So this suggests that at 6 meters, you have a change of either temperature, water ice concentration, or water ice behavior. So if you have a temperature gradient within Cabeus crater with a significant change at 6 meters, that would be very interesting. And I think everyone would really want to know what would be causing that. What is the regolith doing or behaving like in order to cause this weird temperature gradient? If it's water ice concentration, that might tell us a lot about the water ice profile at depth of a permanently shadowed region, which would be extremely interesting. And you would have the concentration increasing at about 6 meters. It also might be a change in water ice behavior, such that the ice at 6 meters is fundamentally different from ice above 6 meters. And so this might be very interesting in terms of, are there different sources of water ice? Are there different water ice behaviors because it's from a different source? It, maybe was deposited differently. And could that be happening at a depth of 6 meters? So I think all of these are really interesting questions. I certainly don't have any information as to, which one would be more likely, but all I'll leave you with is at about 6 meters of depth under Cabeus crater, it looks like something is different than it had been in the 6 meters of regolith before you hit that missing layer.
Hey, Kristen, can I interrupt and ask a quick question? So when you talk about the missing material, so are you saying that no material deeper than 6 meters was excavated? Or
yes.
Okay.
So as far as we can tell, based on fitting the models to the data, the only way to get a good fit with the model is to have all of the material excavated between 6 and 10 meters, have all of that with an albedo set to 0. You can see we tried with this model just to set it to be dimmer, have it be a pure regolith layer underneath a brighter ice layer, and that doesn't fit the data as well either. If you have a solid 1 albedo layer the whole way down, it doesn't fit the data. So in order to match the model to the time series of images, you really have to have just no material excavated after 6 meters.
Got it. Thanks. And then, oh, sorry. One more quick question for me. So the other thing is your 3-layer model in the center there. So I see the ice and I see the bedrock. Is there a 3rd layer that I'm missing?
We have a regolith layer. It fits the data best if that layer has a thickness of 0. So it's technically a 3-layer because we allowed for the possibility of pure regolith, and it doesn't improve the fit to have a layer with any thickness of pure regolith.
Got it. And I see John Gruner has his hand up. So, John, if it's a quick question, go ahead.
All right, thanks. Hi, Kristen. Do you know how deep you have to go before the heat coming out of the moon makes it too warm to have ice to be likely?
I don't know off the top of my head.
Or if anybody does in this crowd, maybe they can put it in the chat. Yeah, I was looking at the thermal heat flux from Apollo, and it seems like just after a handful of meters, the temperature starts to rise. And I'm guessing it's the same at the poles, but of course we're starting from a lot colder temperatures at the surface, so it has a lot farther to rise to get to those temperatures where ice wouldn't be available. So, all right, well, I'll try to find that. Thanks.
Thank you.
Hey, Parvathy, this is Jen. Can I ask a question? I can't find my raise hand button.
Sure. Kristen, is it okay with you if we
Absolutely.
ask? Okay, so Jen, and then I see Carly also has her hand up. So go ahead, Jen, and then Carly.
Okay, thanks. So sorry if I completely missed this, but the Outcross impact probably excavated, depths of 4 to 5 meters maybe, because it's a 20-meter crater. So if the model fitting is based on, fitting surface brightnesses and what was observed in the plume, how are you deducing information deeper than that if, the 6-meter point, if that wasn't even excavated? So it wouldn't be an observation.
So I based this model off of the Hermelin et al. Experiments, and they predicted that that the L-cross would excavate down to a depth of about 10. They mentioned that there may be an overestimation of depths by a factor of 2. So I matched my maximum heights to my maximum depths in my model in order to get these, depths past which we didn't see material. I assumed and ignored the possible overestimation of a factor of 2, but it could be that the scaling factor is overestimated by a factor of 2 based on the Hermelin et al. Predictions. So I guess the answer to your question would then be, as far as I can tell from the model that I used as the basis for my model, it should have excavated to a depth of 10 meters. If it only excavated to 4 or 5, that would agree with what my model is showing, that there was missing material after 6 meters. It could also be possible that my model overestimates the depths from which things are ejected by a factor of 2. But thinking about it a little bit more, I think it's more likely that the actual impact excavated, about 5 meters, and my model is sort of supporting that, that yes, in fact, that's what happened. The model suggested it should excavate down to 10 meters, and it did not. It excavated only to about 6.
Okay, so if it was excavated down to 5, would you just shift your lines on the screen up by a factor of, like, cut them in half?
If you cut them in half, then you would only have, so any material after 3 meters would be missing. I don't know. I haven't really done the work to know exactly how that shift would happen. And the possible overestimation of a factor of 2 has to do with the physics of the actual impact debris plume flow. So that's, it's a little finicky, I believe. So I don't know that it's, it's exactly a factor of 2. It's up to a factor of 2. So I don't know that there's a perfect, equation that will shift it exactly right.
Let me put, I want to ask something very similar to Jen, and I think that's probably where she was going. And that is the importance of the 6 meters here. Because of course, when we go to the poles, how deep are we going to have to drill down to get anything? And you suggest, well, we may have to go pretty deep. So how squishy is that? And you've sort of answered it, that it's model dependent, but it would be good to be thinking about, because in a practical sense, it may have important implications for how you act at when you get to the moon. So you don't have to answer it now, but maybe you can come back to it at the end. We need to let you get through.
Absolutely. And I will say, I certainly think it's not very squishy. I don't think it's, a matter of multiple meters. It may be, off by there are some error bars that are up to about 1 meter. So I wouldn't be surprised if there's some squishiness, as you describe it, of about up to 1 meter in terms of where this actual cutoff is. But I would say no more than about 1 meter.
Okay. Thanks.
All right, so we'll let Kristen continue, and feel free to put questions in the chat and we'll come back to them at the end.
Awesome. Thank you guys for that. So I'm going to talk a little bit about the context in which L-cross happened. So where does the water ice on the moon come from? So there's a lot of possible answers to this. There are interactions between solar wind protons and oxygen and surface rocks, which can form water ice that hops across the surface and ends up in permanently shadowed craters. This source is likely not responsible for large-scale deep deposits. So if you want those large-scale deep deposits, you might be looking at early lunar eruptions, volcanic eruptions. It's unclear if transient atmospheres from these eruptions last long enough for significant volatile deposition. There have been a lot of papers really recently talking about this, and it's a really interesting current field. So that's one possible source. You may also have impacts by asteroids, micrometeorites, comets, which all might deliver water to the lunar surface. And then you have constant impact gardening and water ice escape balancing all of these sources. So what's the likely source? Probably multiple sources. It's probably many things all working together. Deep deposits are likely a mix of, impacts and volcanism. And then you also have a transient water cycle at the surface, likely due to solar wind water deposits. And there's significant interaction between these transient and sequestered deposits, which might complicate any sort of, search we're trying to do for the historical signatures, whether we're looking at the spectra of the water ice, which I believe Paul Lucy did some really great work recently looking at compositions in the L-cross spectra, trying to tease apart, what was the source, impacts or volcanism. That interaction between the transient surface deposits and the deeper sequestered deposits might complicate the search for the historical signatures. So the L-cross 6 meter signature suggests a possible structure at 6 meters of depth, likely not bedrock, possibly due to some sort of ice concentration gradient or stratification, which might be consistent with the recent Cannon et al. In 2020 paper. Any kind of drilling or any kind of radar or the really great orbiters that are being worked on might be able to shed light on these structures, but at 6 meters, like you guys have mentioned already, it's not a super convenient location to get to. So we're looking at this really cool 6 meter structure, but it might be difficult to access. But if we can, on the other hand, if we can get at it, it might have really, really interesting results and tell us something about the historical or evolutionary sources of water ice on the Earth-Moon system, which would be really fascinating. So difficult to get at, possibly very interesting. And then I'm going to talk a little bit about transient water deposits. Recent work by Casey Hannibal has been really fascinating, looking at this diurnally varying, specifically H2O signature, which is a huge step forward. We've known about a varying OH signature, but we weren't sure if it was OH or H2O. So this work was really, really exciting to see come out recently. And so we're looking at this transient surface deposit, and then we also know about these deeper sequestered deposits. And so what I'm interested in, what I'm going to talk a bit about now, is the interaction between these two. And so this is, I'm now pivoting a little bit. I did the L-cross work early in my graduate career, and now I'm going to pivot a little bit to what is becoming, or what has become my dissertation project. So we don't have results for this yet, but hopefully they'll be published very soon. And by very soon, I don't mean next month. So don't be refreshing Icarus too quick. So if we're looking at seasonally shadowed regions, what is a seasonally shadowed region? If you're looking at the little person dancing, in the lunar winter, obviously the whole crater is shadowed. We're at the poles, the sun doesn't get very high. And in the summer, you have this little person seeing just a little bit of sun. This is a seasonally shadowed region versus the permanently shadowed region that never sees any sun at any point. So the seasonally shadowed region is somewhere where the sun rises above the local horizon for at least once, but is hidden during the lunar winter for at least one full month, lunar month. And so you get at least some sun and at least some permanent shadow, or not permanent seasonal shadow. So in order to look at the permanently shadowed regions, they're very hard to access. A seasonally shadowed region might be a more accessible way to learn more about the processes going on in a shadowed lunar region without actually having to go to a permanently shadowed region. And so in a seasonally shadowed region, you have the surface transient water deposits, which are actively moving and interacting all across the surface of the moon, which we know now. And so you have these surface transient water deposits, but when it becomes shadowed, that crater will then temporarily act like a permanently shadowed region. So for the shadowed period of time, the water ice that was a transient water deposit will behave like a sequestered deposit. It'll undergo the same processes as a sequestered deposit. And then once the sun rises again, it'll go back to acting like a transient water deposit. And so the changes undergone during the shadowed period of time might be observable. We might be able to measure what has happened during the shadowed period to this transient water deposit. How has it changed? And that might tell us about the sequestration processes that are going on in all shadowed areas of the moon. And so we're trying to leverage the more easily accessible seasonally shadowed regions and this complex possible interaction and behavior between transient and sequestered deposits in order to better understand the processes affecting water ice profiles in permanently shadowed regions. So in order to do this, I've developed a seasonally shadowed vertical transport model. So this is a dynamical numerical integration model tracking water and thermal vertical profiles in individual locations. So it's the thermal model is based on the local topography. The water model is based on a very simplified solar wind implanted water ice model. And I run it over one lunar year starting in winter so that you see the effects of the sequestration process followed by the effects of returning to a transient state. So I run it in a very rough grid search with a mesh of about 10 kilometers between model points. And I consider ice stable if it's able to survive one lunar year. So this is really important. I'm not considering impacts. I'm not looking at micrometeorites. I'm only looking at a thermal environment in this model. So when I call ice stable, I am definitely not suggesting that this is actually a stable sequestered deposit because there are significant processes that I'm simply not accounting for in this model. And so what I'm looking for is I'm exploring possible water ice behaviors and vertical profiles, trying to understand what kinds of behavior we might have as the transient water ice engages in sequestration processes and then returns to a transient state. What kinds of behaviors are we possibly looking at? And could any of these be leveraged in order to help us better understand sequestration processes in general within lunar shadowed regions? So this is kind of a roadmap to the model. The gray boxes are the inputs, and then the blue boxes are where I track water ice migration, vertical transport, and the orange boxes are where I'm tracking, surface temperature and the vertical temperature profile as the temperature propagates downwards. So you can see there's a lot of interactions, and I run this on a very fine time scale to capture all those interactions. As the temperature changes, the thermal conductivity will change, which changes how the temperature changes, which changes how that affects the water ice. So it has to be a very fine time scale in order to capture those processes. So my first step is I'm looking at a simplified one-dimensional global water, solar, wind, global solar wind water ice model. And so what I'm talking about here is the lunar water cycle starting with solar wind delivery. And so you have solar wind delivery at the surface, the water ice moves in a ballistic trajectory and may land in a permanently shadowed region. If it's liberated by any sort of temperature increase, it will then be added back into the ballistic trajectory pool. So I'm looking at this process in a very simplified way. When I say one-dimensional, my one dimension is latitude. I'm only looking at particles moving in and out of latitude bins in a random ballistic trajectory. And so I'm not looking at any sort of local topography. I'm not looking at a day-night cycle, I'm only looking at, incoming water ice particles ballistically hopping randomly in random directions. And the output for this super simplified water cycle model is just how many are landing at a given latitude at a given time. So it's a simplified model with a simplified output. And I'm just using that as a basis for, how much water ice is landing at a given latitude versus another latitude. The next step, once I have my input for how much water ice is landing, the next input is, well, what's the temperature? And so for that, I'm looking at when is the sun above the horizon, how much radiation is delivered, so how high in the sky is the sun, what are the properties of the lunar surface, any other sources of heating, the surface emissivity. And so that's just calculating the surface temperature at any given time. And so in order to find the local horizon, I'm using LOLA digital elevation models. And so here I've plotted LOLA digital elevation maps, and I've also marked which craters I'm looking at in this study. I'll talk a little bit more about why I chose these locations later, but I calculate the horizon profiles by finding the highest angle in every direction from a central point. And in order to calculate them, I'm using the method described in Mazzarico et al. 2011. And so here I show horizon profiles for Cabeus crater. This one is a seasonally shadowed region. You'll see the sun just rises above the horizon in the summer and does not touch the horizon during the winter. So a very proper seasonally shadowed crater. And here I show a permanently shadowed crater for comparison. You see the sun never touches the horizon. This is a crater that will just never see the sun. And here I show, once you have your surface profile or surface temperature changes, those temperature changes need to propagate downwards. So that depends on thermal conductivity, specific heat, density, all of which change with depth and temperature. So again, find time scale in order to capture those interchanges. So once you have a change at the surface, it'll take minutes to reach ice buried even 10 centimeters beneath the surface. That time lag in escaping ice may possibly be unobservable. So I believe Close et al. Recently published a paper about seasonally shadowed regions as a reservoir for the ice landing in permanently shadowed regions. One possible observable would be looking at a time lag in escaping ice from seasonally shadowed regions. Any sort of time lag might suggest vertical migration, which might tell us a lot about, well, how quickly is this vertical migration happening? So when I chose my locations, I took a lot of things into account. I wanted a diverse set of locations, and I wanted locations that had some probability of having ice. I looked at the Cannon et al. In 2020 Ice Favorability Index. I looked at neutron suppression signatures, and I looked for interesting thermal signatures across the crater floor. So I was looking for really interesting, complex, rich, geologically significant and distinct types of craters. So my first selection was, of course, Cabeus crater. We know for a fact Cabeus has water ice, and we know it has really great permanently shadowed regions. So as a boundary case, this is a region we know has ice, we know has permanently shadowed regions, and I selected it because it would ground the rest of the craters with some kind of easy to understand results. If we're looking at a permanently shadowed region, we should know what that looks like. I also chose the Hayworth, Shoemaker, and Faustini craters, as well as the ridges in between them. These craters have really interesting complex topography, complex ice favorability index matrices. You have these great neutron signatures in 2 of those craters. And so I was really interested in looking at how across these 3 craters at these very high latitudes, what kind of variation are we looking for? Are we looking at an ice or an ice behavior and the variability between the various locations? So these are really interesting locations, and they've been mentioned several times as targets of possible human exploration. So I thought these would be a really great and interesting place to look for possible water ice behaviors. I also chose Amundsen crater. Amundsen has this really beautiful thermal gradient across its crater floor, which is very interesting. It does have a possibility of having water ice at some locations on its crater floor. It has a lot of interesting local topography, and it's this really huge crater, which I thought would be an interesting diverse profile across its crater floor. I also chose Idelson L, which is the opposite of Amundsen in a lot of ways. It's a lot smaller. It's a lot less, it has a lot less of a complex signature across its crater floor because it doesn't have nearly as much crater floor to have a complex signature in. So I thought it would be an interesting comparison to Amundsen to go for a much smaller crater. I also chose Hale Q, which as you can see is not even on this map. It has a latitude of, I believe, about 76. So this is a much lower latitude, or I guess lower latitude, sorry. It has a much lower latitude than any of the other craters, and it really shouldn't have water ice. So I chose this as, again, a counterpoint to Idelson L, a counterpoint to Cabeus crater. This should be a location that should not have water ice, and we should know that the water ice should behave in a way that's not at all surprising. Namely, it really shouldn't be there for very long. So again, this is a way to check the model results against what we suspect we already know. So when I run my model for these locations, and I'll state here, I have not finished running the models. I have several locations finished, but not all. I've found 4 archetypes of water ice behavior. So the first archetype, no one's surprised, permanently shadowed regions. There's no sunrises. You get a sequestered deposit. It steadily migrates downwards. There's nothing transient about this location. I also have seasonally shadowed regions where we have anywhere between 1 and 11 sunrises. You get sequestered deposits. You also get transient deposits, and we're looking at the interactions between the two. I found 2 archetypes in non-shadowed regions, which surprised me. I found a non-shadow type A, which is exactly what we expect. There's 12 sunrises, there's nothing sequestered, all the ice is transient. And then I also found the surprising non-shadowed type B, which somehow does develop a sequestered deposit underneath the transient deposit. And those interact over the course of the lunar year. And I found this very surprising, and I'm really excited to show you this archetype of possible water ice behavior. And I'd like to clarify before I show you any of these, that I am not suggesting that these are ground truth. I am not suggesting that this is actually the case on any of these locations. Again, I'm not including any sort of impacts. I'm not including a number of different possible complicating factors. So I'm not suggesting that any of these locations, if you went there and dug, that you would actually find this water ice profile. This is just exploring possible water ice behaviors that could be exploited on a short time scale in order to learn more about sequestration processes. So here is the permanently shadowed region. You can see the sun doesn't get anywhere near the horizon. This is in Cabeus crater. You get, at the end of the model run, a very smooth vertical distribution of water ice. And you can see the heat scale here is water ice mass. It just increases over time, right? It migrates downwards and more is landing at the surface. So you just get this triangular shaded region. Very simple, very easy to understand. Pretty much exactly what we expected. If we're looking at non-shadow type A, this is the opposite case. This is for Hale Q crater. You get 12 sunrises. The ice will migrate downwards during the lunar night, and then pretty much immediately is excavated as soon as the sun rises. And you have 12 of these triangular signatures, very much as expected. The sun is never below the horizon at any point during the year. You get a tiny peak, but at a small enough mass that it's essentially a random remnant, right? So this little peak is not what I would consider an actual suggestion of a sequestered deposit. There's nothing going on in the overtime ice mass tracking plot to suggest any sort of real interaction between sequestered and transient. So here we have seasonally shadowed regions. You see, instead of just a triangle, you see this sort of sawtooth signature extending downwards when the transient material at the surface has been liberated. It's been heated and escaped the surface, but some of the ice, you can see this shading, especially down here in this one, you have a somewhat stable sequestered deposit that is interacting with the transient surface ice. And so these are really exciting locations. You have in the final vertical ice profile, you have the smooth distribution, and then you also have these shoulders down at about 10 to 50 centimeters of older material, water ice that has survived sunrises. And so this is exactly what I was hoping to find. This is what I hypothesized I might see. These great sawtooth features and these shoulders of water ice are suggesting sequestered deposits. Again, not necessarily in reality. I'm not including any sort of impact gardening, but this is just a possible water ice behavior that's really interesting. When you look at these sequestered deposits and you look at the transient deposition, and these transient deposits will migrate downwards, interact with the, oops, sorry. Oh, sorry about that. Well, the transient deposits will migrate downwards, interact with these sequestered deposits, and then be reliberated again. So that interaction between the transient and the sequestered is what I think is this really interesting indication that we might possibly be able to leverage these exact situations and these exact conditions in order to better understand sequestration processes and vertical migration processes, which I think is really exciting. If you look at this plot here, you can see these little double peak signatures. This is directly corresponding to the sun rising above the horizon here and then later here. So you can see all of these water ice liberation signatures are directly tied to the sun rising above the horizon and then the temperature propagating downwards. So you can see there's actually some really, it's very sensitive to when the sun rises and when the temperatures change. And so when you get this double rise feature here, like you have in this Amundsen crater location, you can get some really interesting results and some really interesting signatures. So again, I think this is a really great result. It's highly suggestive that this might be a fruitful avenue for exploration and for study to try to understand what happens beneath the surface of shadowed areas. And here I have no shadow type B. Again, this is the surprising one. This is the one I didn't expect to see at all. But you can see this haze of water ice that somehow is just deep enough that the sunrises don't cause it to be liberated and to escape. And so you have this little haze of shadow deposit. You can see the shoulder is much less in proportion to the actual transient deposit. So a lot less of the water ice in these no shadow type B locations becomes this sequestered deposit compared to the seasonally shadowed regions. This one I thought was really interesting. This is a Hayworth crater location, very high latitude, and it looks like a seasonally shadowed region, but the sun is actually rising every time, and you can actually see very faint gray shadows indicating here sunrises, and the sun just doesn't get high enough to heat it very much. So you have minimal water ice escape during the lunar winter, even though you actually have 12 sunrises in this location. So I thought this one was really, really interesting. It's suggesting that at the very high latitudes, the game changes a little bit. You're not just looking at no shadow type B, you're looking at no shadow type B that looks exactly like seasonal shadow unless you look a little bit closer. So I thought this one was really interesting as well. And so here I have color-coded the various types. So blue is permanent shadow, teal is seasonal shadow, red is no shadow type A. Remember, that's the one with no stable ice. And orange is no shadow type B, which is the locations where you have 12 sunrises, but still some kind of sequestered deposit. And so if you're looking at the geological locations where we have these various types, There's a lot of spatial variation. What I think is really interesting is looking at the Hayworth, Shoemaker, Faustini. You have the no shadow type B lining up exactly on the ridges between the various locations. So I think that's very interesting. There's a lot of this spatial variation, but it does seem like they're falling very naturally into different local topography categories. So, no shadow type B looks like it's up on a ridge, up on a slope. You have seasonally shadowed and permanently shadowed tend to lie together, tend to be located in similar locations. And of course, you have Idelson L, Hale Q are no shadow type A, pretty much as expected. So the black points are the ones that I haven't modeled yet. So this plot will continue to fill out as I continue to model these locations. So conclusions, there's a lot of limitations to my seasonally shadowed region model. It's computationally expensive for one, but for another, I make a lot of simplifying assumptions. I'm assuming that the surface that the sunlight is hitting is flat. There's no slope to it. There's constant albedo across every location in my model. There's a constant emissivity. There's constant densities. Well, there's a vertical density profile, but they all have the same one. There's a constant water ice migration rate. And so these are all really not true to life, right? These are simplifying assumptions that maybe are not giving me a completely accurate view of reality. And I'm not trying to get a completely accurate view of reality. I use a very simplified water cycle model that's just giving me an input of, water ice per second per square meter, depending on latitude. I'm treating the locations as completely isolated. There's no horizontal interactions with a different location. I'm not including any sort of micrometeorite. I'm not including any ejecta covering anything or covering the surface from a nearby impact. There's no impact gardening whatsoever. I've mentioned this several times because it's very significant. This is really, really short time scale model. I'm not trying to model over a long period of time. I'm not trying to suggest that anything would be stable for geological timescales. So my model results are really intended to serve as a reference for possible water ice behaviors, and any predictions for water ice deposits should definitely not be interpreted as me trying to say that they actually exist. What I'm trying to do with this model is explore possible water ice behaviors and talk about how these possible behaviors, particularly the interactions between the transient surface deposits and anything a little bit more sequestered, how that might give us leverage in order to better understand sequestration processes and the various vertical transport processes going on in lunar shadowed regions. So in the future, not in this immediate work, but if this model wants to be at any point is improved, these are possible model additions. And if anybody wants to collaborate on any of these improvements to the model, I would be very open to doing so. I know a lot of people have done incredible work already on really all of these facets of understanding lunar environment. So looking at scattered light, variable angle of impact based on local topography, is it slanted? Is it completely flat? Looking at any smaller scale features and incorporating those into the local horizon calculation. And so that would be looking at smaller scale cold traps like the one Hain et al. Recently talked about, micro cold traps. I haven't incorporated that into this model either, but that's something that could be really interesting in the future. Looking at horizontal thermal profiles, so allowing locations to interact with one another at depth. Looking at the actual precise albedo of the location, looking at thermal conductivity and albedo tied to changing water ice content would be really interesting. Of course, looking at micrometeorite impacts and impact gardening would be crucial if I want to ever look at a longer time scale for this model. And then looking at, variable incoming water ice fluxes, looking at initial conditions, including pre-existing sequestered deposits. These are all possible future work, but are not going to be incorporated into the model in the immediate future. So in summary, I'm going to bring you back to the L-cross model very briefly. There's missing material of unknown composition below about 6 meters. And again, that's 6 meters plus or minus about 0.75 meters, which might provide possible insight into a deeper ancient water ice deposit. And if you want more information about that model, you can find it in this paper here. And then I'm also looking at the SSR model, which is providing sort of this top level exploration of water ice behavior across diverse lunar polar conditions. And I found 4 water ice behavior archetypes, one of which was surprising and 2 of which are extremely interesting, but all of which kind of tell us a lot about what is the story when we're looking at the interaction between transient and sequestered water ice deposits. And the complex interactions between those deposits might provide insight into ongoing sequestration processes in all lunar shadowed regions, which would be really exciting and interesting to look into, especially with all of the upcoming lunar exploration that's been talked about for a while now. This, I think, would be a really exciting location for further study. I'd like to thank the New Mexico State University High Performance Computing Group, which supported the modeling efforts for the seasonally shadowed model. And I'll take any questions at this point.
All right, thanks, Kristen. That was a great presentation.
Thank you.
You have a ton of questions, and since there are so many, your excellent advisor, Dr. Nancy Chanover, has volunteered to collect the questions and pass them along to you afterwards. I do want to leave a bit of time for people to talk about upcoming LPSE presentations, but I am going to pick one question. So since we had a lot of questions about the L-Cross work, I'm going to, the one question we're going to do live is from Julie Mitchell, who asks, do you think there could be some transient migration of volatiles from SSRs to PSRs as volatiles are added to SSRs throughout a year? So Julie says it seems like SSRs might get warm and some volatiles might migrate from them into nearby PSRs.
So I will refer to, there was a really great paper published by Jacob Close, and he looked into that in a lot of detail. And I definitely recommend that paper that looked at exactly that question. And I believe his results did suggest that there was significant collecting of water ice in the seasonally shadowed regions, followed by migration of that collected material directly to PSRs. And so you do get an increase of material migrating to PSRs when seasonally shadowed regions warm up. Absolutely.
Awesome, thank you.
All right, and we actually have Jacob online, and I think it was almost a year ago we had him talk about his paper on this call as well. So thanks for reminding me about that, Kristen. And Jacob, if you want to, put a link to your paper in the chat,
Yeah.
I'm sure people would appreciate that.
Yeah, I was just in the process of doing that, so I'll do that right now.
Awesome. All right, so in the 5 minutes we have remaining, before that, thanks again, Kristen. That was
Absolutely.
a really good presentation, really interesting work, and yep, good luck with the rest of your PhD, and we'll have you back to talk more about the seasonally shadowed stuff once that's published.
Thank you very much.
But in the 5 minutes we have left, LPSC presentations and posters went live earlier today. So the conference is going to be not this week, but the week after. So I just wanted to have some time open on the agenda for anyone to mention any upcoming presentations that they might have. And, in fact, I'm going to go first. So some undergraduate interns who've been working with me over the last year have a poster in the Lunar Volatiles poster session, and they've been looking at differences in how different isotopologues of water, so H2O and HDO, they've been modeling differences in how those might be transported and deposited at cold traps. So that's in the Lunar Volatiles poster session. So that's one I would highly recommend checking out. But who else? I know we have a bunch of people, and I have seen many names on the agenda. So does anyone else want to highlight any presentations that they or colleagues might be giving?
This is Julie. I have a talk about Artemis curation. So it's a little bit not so much looking into volatile science specifically, but how we can facilitate it with sample return. There's a pretty big volatile component in there. So
Awesome. Who else?
John Keller. I'll mention our sputtering work that I'm going to report on. It's not in the title because we kind of found this late in the game, but we think we see a low energy, kind of a distinct low temperature sputtering component that comes up. So that's what we'll discuss.
What's that being sputtered?
So we were looking at negative ions being sputtered, but we were doing the velocity distribution, and the classic velocity distribution that you might have seen comes out at around 10 EVs, but we see a distinct lower temperature population at around 1 to 2 EVs.
oh.
Rosemary, were you about to say something?
Yeah, I just wanted to ask John, what is the number of their poster?
I think it's off the top of my head. I think it's 1522. It's a talk in the exosphere. I think it's exosphere session, or is it volatiles? I don't remember. Sorry.
Okay, I'll find it.
Yeah.
A student who's working with me, Elizabeth Fisher, will be doing a laboratory Hapke modeling to try to separate surface adsorbed water to body component water. So I'm sure she'd be very interested in hearing comments that anyone has about those experiments.
Ah, interesting. Yeah. Thanks for sharing that, Carly.
This is Casey Honeyball. Along those lines, I'll be sharing IRTF observations of central peaks, showing some with enhanced hydration, looking for like internal water.
Cool.
And Jose Grava here. I have a poster on LAMP observations of the lunar exotic helium, summarizing a paper we just published this month on the monthly notices of the Earth Society, and it's looking at helium in extreme ultraviolet wavelength.
Awesome. Thanks, Cesare. All right, so we are at the hour. I know there are more posters, but in the interest of time, I am going to conclude for today. But I think what I'll try and do is get a thread going via email, and feel free to add on to that, and so we can try and round up via email posters and presentations, so that it's easier to navigate the abundance of material that's online. But with that, I think we will call it a day for today. So thanks again, Kristen. And thanks everyone for dialing in and highlighting your posters. And we will meet again about a month from now. Take care, everyone.
Thank you.
Thank you.
Bye. Bye.